Hello everyone, today I'll be talking about symmetry in functions, the graphical approach and the algebraic approach. Okay, so I want you to brainstorm, what do you think symmetry means to you? And we'll go ahead and talk about it. So pretty much when someone thinks about symmetry, they usually think about, oh, well, something that's the same on the left side, right-hand side, top or bottom, diagonally, and whatnot. So a nice example that we have is the Batman symbol, left-hand side and the right-hand side. You can see that they're identical. And we can see this letter right here, the letter B, that the top is the same as the bottom. If I was to go ahead and fold that B, they land right on top of each other. And that's a nice reference that I'm going to be using throughout the lesson. Okay, what I also like to show you is this right here, the letter H in this scenario. It is the same on the left and the right, and it is also the same on the top and on bottom, on the top, whoops, on the top and on the bottom. So whenever they meet that scenario, a graph, a function, an image, pretty much they are symmetrical diagonally, or about the origin, if you would. So this is what we're going to go ahead and talk about today. That if something is symmetrical left and right, it is even. If something is symmetrical top and bottom, that we're going to go ahead and see that is not a function. And if something is diagonal about the origin, meaning diagonally in the quadrant 1 and 4 or 2 and 3, they are odd symmetry. And we'll see this right now. So the best way I can explain this is by showing you a point on a quadrant 1. Let's say this is quadrant 1, whoops, quadrant 1, quadrant 2, quadrant 3, quadrant 4. All right. I just want you to pretend this point is somewhere on a graph, okay? So this is just a portion of the graph. Now, if I have this point right here, and a lot of people like to say this when you fold a piece of paper right across the y-axis, just so we're all on the same page, x-axis. If I fold it exactly halfway, we can see that this point will eventually land over here, right? Giving me, let's put a letter on this. I don't know, let's say it's Q. Okay, so if this point went to the left-hand side, because of my hot dog style that I just pretty much folded my paper, I can see that the height stayed the same. So my y is still positive. However, this area right here, let me get my laser pointer. This area right here, the x's are negative, right? Because it's going in the left direction. So this has to be a negative. And I'll go ahead and put this red, negative x, right? Now, so whenever something like this happens, this is symmetry is even. So whenever something like this, it is even symmetry. When my point on my x, it just becomes negative x. So the values stay the same, but the x is just negative and the y stays the same. And I'll summarize it in the next slide. So pretty much if we have something like this, what the heck, if we have something like that, we have our, there you go. If we have something like this, the points are in quadrant 1 and quadrant 2, and they landed on top of each other, they are even symmetry. Okay. What if something is symmetrical about the x-axis? So let's name that S, right? So let's go ahead and put a point right here. Say it is S. So this is like your hamburger style, right? If I get my piece of paper and I fold it hamburger style across the x-axis, I can see that this point just dropped down, right? Dropped down all the way there. So my axis, my horizontal distance stays the same. So my x stays positive. But what happens to my y? My y used to be in quadrant 1, and then it dropped all the way to the bottom. So that's negative y. Okay. And the last example I have is diagonally. Okay, oops. So let's say I do my hot dog style and then my hamburger style. So I do it this way, right? And then I get a point right here, and then I do it again. It's very messy. Ideally, I went ahead and got this new point, this negative x, y, and then I reflected it, so I got the horizontal distance for the x is negative, and the y dropped all the way down, so it's negative y. So you can name that another point. Let's call it w, if you will. Whenever something is diagonal like this, right? Diagonal across the origin, where as you can see in my definition, both x and y axis symmetry, this is odd, okay? So just to summarize everything here, if something is symmetrical, let's go ahead and say notes. If something is symmetrical, on the, let's say like this case, the origin, it is odd. If something is symmetrical about the y-axis, meaning the left and the right, this is even. And if it is symmetrical about the x-axis, you know, like top and bottom hamburger style, it is not, because it does not pass the vertical line test. And we'll see some examples right now. So this one right here, take a second to look at it, and you can pause the video if you want to. And I want you to think, what type of symmetry does this have? So I see the top of this function looks exactly the same as the bottom. So if I do a hamburger style, I can see that my top is the same as the bottom, and it's symmetrical about the x-axis. So however, it's symmetrical for sure, but can I see right here, it does not pass the vertical line test. So this is not a function. Even though it's symmetrical, it's not a function. So a lot of stuff, we have to do a lot of stuff here. When you see it's not a function, you don't have to find the domain and whatnot. Okay. So let's get to the good stuff. Let's look at this one right here. This happy face parabola is quadratic. We can see that it is symmetrical about the y-axis. My left is equal to my right. So therefore, whenever that happens, it is even. When it is symmetrical about the y-axis. Easy peasy, right? Okay, the next one right here, we can see that I have a point right here, and I have a point right here on this function. So if I get to see that it is symmetrical diagonal, so across the quadrant, so quadrant 1, and this would be 3, and quadrant 2, and 4. If they're symmetrical diagonally, this is odd. So odd because they're symmetrical about the origin. Okay. Alrighty. So this right here is 3 examples. So go ahead and pause the video and give them a try. And then I'll give you the solutions right now. Okay, so on this one we can see that diagonally they are the same, right? So this is odd because it is symmetrical of the origin. There you go. This time I spelled it right. You can see this one. We could pick a random dot. Let's say right here. And the left-hand side and the right-hand side look the same. If I do hot dog style, I can see that the graph lands on top of each other. So this is symmetrical about the y-axis. Therefore, it is even. Last but not least, okay. Assuming this graph does not overlap, right? We can see that the left-hand side, oops, and the right-hand side are the same, just like the last example, so it's symmetrical about the y-axis. So therefore, it is even. So hopefully you got those right. All right, 3 more examples. So go ahead and pause the video right now, give them a try, and I'll talk about them right now. Okay. Very, very similar if they are the same diagonally. So this would have worked here, or it could even have worked like that. Whoops, not very symmetrical, right? But ideally it's the same thing, right? It's diagonally, so therefore it is odd because it is symmetrical about the origin. Ooh, dilemma. How about this one right here? I can see that the graph only exists right here in quadrant 1. Is there anything I could compare to on the left-hand side, on the right-hand side? I'm sorry, or below? Well, there's not much graph to do. There's nothing here. There's nothing anywhere here. So therefore, this is a none. We can't compare symmetries. So therefore, not symmetrical. We don't have no clue. Not to be confused with a function. This is a function. It's just not symmetrical. There's nothing we can compare it to. And the last one, easy peasy. We get to see the left and the right. This is symmetrical about the y-axis right here, right? So therefore, it must be even Steven. Awesome. Okay. I do want to go ahead and talk about algebraic as well. So these are the notes for how to check if they are symmetrical using algebra. And all you have to do is substitute this negative x into the function and evaluate. If the function provides the original function, it is even. Pretty much left equals to right. So if you substitute a value in there and it gives you the same output, it's even. It's odd if all the signs changes. So negatives turns positive, positive turns negative. That's how you know it's odd. Neither, that just means none of that happened. Like maybe one sign changed or something like that. It sounds very, very complicated, but it really isn't. Okay, so let's do the first one. All I want you to know is that you're substituting a negative x. So you're substituting a negative x into all the x's. So in this case, I got x squared plus 1. So instead of writing x, I'm going to go parentheses squared plus 1. And remind me again, what are we substituting? Well, it's this negative x on negative x. So I just evaluate. That's the same thing as saying negative x times negative x plus 1. Negative times negative gives me a positive, and x times x gives me an x squared. So notice how this is my output, is my answer, and it's the same as this answer. So what did we just say on the last slide? If they are the same, they are even. If they are the same, you substitute and they give you the same, they are even. All right, guys, let's do the next one. Oops. I got x cubed minus 4x. I do the exact same thing, guys. Let's get black. So I get x cubed minus 4 times x. I'm leaving them blank because I'm going to substitute this negative x into all my x's. Okay. So this is the same thing as saying negative x times negative x times negative x minus 4 times negative x. So I'm going to go ahead and simplify the best that I can. So I got a negative times a negative times a negative. Well, that's just negative, right? And then an x times an x times an x. This should give you x cubed. Okay, last but not least, I got a negative 4 times a negative x. That's negative times negative. That's a positive 4x. Okay, so let's compare this solution that I just got, versus the original that we had. And we're going to see, are they exactly the same? Let me get my laser pointer. And I want you to see right here, this x cubed is now a negative x cubed. Okay, that's good. And then this negative 4x is now a positive 4x. So therefore, do all the signs change? Yeah, the positive went negative and the negative went positive for every case. So therefore, this right here is a, can't get my marker, is a odd function. It's an odd function, and then the first one was an even. Okay, so the first one was even because they were exactly the same, even after I substituted. The other one is odd because every sign changed. Well, hopefully you have a different question right now coming up. Well, then how do I know that they're not, that they're neither or whatever? Well, good question. Um, let's say for example, let's say alternative example, in a different universe, in a parallel universe, we got that oops, that this right here, x cubed, and it gave me a minus 4x. Let's say in a parallel universe, we got this solution. Well, I do the same thing. I go ahead and compare my answers. But now when I try to compare it, I see that only one sign changed. Let me get my laser. This x cubed is positive. This one's negative. We're off to a good start. But this negative 4x stayed negative. So therefore, you can see that, hey, it didn't match exactly what I wanted. It didn't stay the same, so it wasn't even. Not everything changed, so it wasn't odd. So this one is a neither, a none. So that's how you know these three different cases. That if they're all the same, they're even. If they're everything changes sign, it's odd. And if the function just does something whack, it's none. Thank you for your time, guys. That is the end for this video.